Greetings and welcome to another installment of QuantSlob. This is 28 in our basic application series. This time around we pick up our ongoing series, The Basics of Counting, with 4. It turns out that we can combine these two hopefully familiar concepts and arrive at one of the most, if not the most, important distributions in all of science. Certainly among discrete distributions. But as a fair heads up, getting to our destination in this video is going to involve some mental somersaults. It's a little mind-bendy, so to say, so just hang in there. Let's return to our beloved pizzas. If we have a total of 6 available toppings, we can make a total of 64 different pizzas. And if we look at Pascal's triangle and ignore the apex, 64 is the sum of the numbers in row 6. It is also 2 raised to the power of 6. In fact, the row totals in Pascal's triangle equal 2 raised to the power of the row index. So let us imagine that someone has ordered one of each type of pizza made from our 6 available toppings. If someone were to ask what proportion of these pizzas have exactly 3 toppings, we can get to our answer directly. There are 20 pizzas with 3 toppings and a total of 64 pizzas. Therefore, our answer is 20 divided by 64, or simply 5/16. This is direct here because the 6 toppings are evenly distributed among our pizzas. After all, there is 1 of each type of pizza. Okay, so that's not going to win anyone a Nobel Prize here, but things do get more interesting. Suppose now someone were to ask what proportion of our 64 pizzas have garlic. Well, it turns out that 1/2 of our pizzas have garlic, 32 of them. And it turns out that this is true for all of our toppings. 1/2 have onion, 1/2 have salami, and so on. So is this obvious? Well, we can kind of come to understand why this works by noting that if we exclude garlic originally so that we have only 5 available toppings, there are 2 to the 5th, or 32 total pizzas we can make. And if we add another topping, garlic for example, as we already know, there are 64 total pizzas we can make. Therefore, it is fairly reasonable to understand that 32 of these pizzas, or 1/2 of the 64, have garlic. Gets better. Suppose we set aside all the 32 pizzas with garlic and someone were to ask what proportion of these have salami. Well, it turns out the answer is the same, 1/2. That is, of our 32 pizzas with garlic, 16 also have salami. Or said another way, given that a pizza has garlic, the proportion with salami is 1/2. And if we were to set aside all the pizzas that have garlic and salami, all 16 of them, and someone were to ask what proportion of these have, say, mushroom, the answer is the same, 1/2. Just to clarify the symbology here, this statement here could be read as the proportion of objects, in our case pizzas, that have mushroom, given that they have garlic and salami, is 1/2. Another way to say this conversationally might be something like, of all the pizzas that contain garlic and salami, 1/2 also contain mushroom. Now, if we subset our pizzas based on the presence of any, none, 1, 2, 3, or 4, or 5 toppings, and ask what proportion of these contain one of the other toppings, the answer is always going to be 1/2. So, to help us get to the punchline for this video, we're going to do something that on its face may seem to really complicate things. We're going to completely reverse our approach. Instead of defining our collection of pizzas ahead of time, like 1 of each kind of pizza, we're going to specify the constant prevalence of each and every topping, then see what sort of collection of pizzas we end up with. So for example, we're still going to use our 6 available toppings, but suppose now that the proportion of pizzas containing any given topping is not 1/2, but rather, say for the sake of example, 2/3. 2/3. That is, if we consider only pizzas with a pre-specified subset of toppings, the proportion of those containing one of the other toppings is always going to be 2/3. Now, suppose someone were to ask what proportion of this new collection of pizzas has, for example, exactly 3 toppings. And you may think that this is just insane. I mean, no human being, or even like some sort of super pizza being, could ever solve a problem like this. But just when we think all is lost, well, I have to confess, we struggled coming up with the metaphor. I mean, I think that this is okay. Mr. Combination meets Miss Proportion. They seem pretty happy here. We also considered, hey, you got some proportion in my combination. No, you got some combination in my proportion. But, you know, who's going to get that reference? And honestly, I'm far from convinced that that is even amusing. Anyway, what do we end up with? Behold the binomial function, or the binomial distribution function. So let's break this down. Let's drill into this here. Okay, so here we input the number of pizza toppings, and we also input the total number of available toppings along with our proportion representing the constant prevalence of any one topping. And the function hands us back the proportion of pizzas within our collection with the specified number of toppings. So now let's make use of this on our original setup, where we have a collection of one of each kind of pizza. 6 choose 3 is 20. 2 times itself 3 times 2 times itself 3 times is 64. 20 over 64, which simplifies to 5/16. We already know that. Same answer as before. But now let's try this with our new collection of pizzas. Okay, so 6 choose 3 is still 20. Combination part stays the same. 2/3 times itself 3 times is 8 over 27. 1/3 times itself 3 times is 1 over 27. So our answer here ultimately is 160 over 729. There's no common integer factors, so this does not simplify. In decimal form, we have about 0.2195, or a smidge under 22%. So check this out now. Interesting, when the constant prevalence of each topping in our collection is 1/2, the proportion of 3 topping pizzas is greater than when the prevalence of each topping is 2/3. I mean, after all, 31% is greater than 22%. Now, we can summarize our 2 collections of pizzas using a table to show the distributions of number of toppings. So here, K is the number of toppings. The next column, the middle column, shows the proportion of pizzas for each of the possible number of toppings, where the prevalence of each and every topping is 1/2. Our original collection of 64 pizzas we've been working with originally would be an example of this. The far right column here shows the proportion of pizzas for each of the possible number of toppings, where the prevalence of each and every topping is 2/3. Most recent example. Notice that no topping pizzas, 1 topping pizzas, 2 topping pizzas, and 3 topping pizzas are more popular within our first collection compared with our second collection. And the opposite is true for 4, 5, and 6 topping pizzas. By popular, we can also call the numbers here in the middle and right column relative frequency. Now, before we close out this installment, and we're also closing out season 3 of QuantSlob, an exciting new feature here, our QuantSlob challenge. Okay, ready? Suppose the prevalence of each and every of our 6 toppings is not 1/2, nor 2/3, but rather 1. What sort of collection of pizzas might we have, and what might the distribution of number of toppings of such a collection look like? We're going to pick this up with our soon upcoming season 4 kicker, part 1 of summarizing data. And that's it. That's going to do it this time around. It was a really fun first 3 seasons of QuantSlob. Thank you very much for being a part of it. Whatever you do, don't forget to stay tuned for more QuantSlob.